the same confined space, there is an infinite number of parallel realities that actually can create a powerful or a less powerful form of God equals MC squared as we know it.
What if a single conversation could make us rethink everything we know about space? Deep under Switzerland, a ring of powerful magnets sends beams of particles racing at almost light speed. Some claim those collisions have torn open a doorway to another world. Today, we explore that rumor through the eyes of Joe Rogan and a 13-year-old kid. We ask the questions that create wonder, seek the facts that ground us, and follow a path from rumor to reality. But this wasn't just a feel-good interview with a smart kid. As the conversation unfolded, something strange happened. Something that made even Rogan pause. Was Max seeing patterns no one else could? Why Joe Rogan brought in a genius kid? When Joe Rogan learned about Max Laughlin's physics videos, he reached out immediately. Max is 13 and shares under @MaxLaughlin on TikTok. His short clips cover memory quirks and particle collisions. One video on the Mandela effect using colored cards has hit over 5 million views.
If there are other universes, they're next to ours, and this actually relates to my theory of the Mandela effect and how the particle accelerator altered the weight of one.
It caught people's attention, which led to his video being widely shared. In February 2025, producers invited him to appear on episode 1912 of the Joe Rogan Experience. Max spent 2 weeks studying official CERN reports and watching brief LHC documentaries. On April 10th, he flew into Los Angeles for the show, where he met Joe Rogan with his crew. They moved to the set, a simple studio with 2 chairs and a round table. As cameras rolled, Rogan introduced Max as someone who explains tough ideas clearly. He then asked how Max first discovered his interest in science. Max said he built a telescope at age 8 to see moon craters. Next, he assembled a radio with soldering tools to learn electronics basics. Max also won first place at his county science fair for a homemade cloud chamber that showed particle paths. Rogan brought up the portal claim tied to CERN's collider. Max described the facility as a 27-kilometer ring under Geneva for proton collisions. He explained that the goal is to recreate early universe conditions and search for new particles. He added that CERN posts every result online, and no portal report appears. Rogan remarked on how fast rumors spread on social media. He asked how Max verifies odd claims. Max replied that he checks lab websites first. He also reads articles on well-known physics blogs and watches lecture recordings by university researchers. During the talk, Max sketched a basic layout of the collider on paper. Their chat stayed focused on facts. Rogan said Max had reviewed dozens of summaries from high-energy physics groups before arriving. Max Laughlin is a genius. No way a 13-year-old kid could have so much knowledge about complex matters. It is very rare. Almost 1 in a million. Through him, a whole discussion has been created by science giants trying to understand and explain what is really behind Max's revelation. But here's the twist. Max wasn't just parroting facts. He spoke with the calm confidence of someone who saw something he couldn't unsee. So, what exactly did he uncover? Inside CERN, what really happened underground? Inside CERN, a tunnel runs below fields near Geneva, at the border of France and Switzerland. It stretches for 27 kilometers in a circular path. Inside that ring, machines work day and night. They keep the space cold using liquid helium. The temperature drops to minus 271 degrees Celsius. That is colder than deep space. Superconducting magnets sit along the walls to guide particles. They shape the path for beams of protons on a steady track. Protons flow in 2 separate beams that circle in opposite directions. Powerful radio waves push them faster on each lap. Sensors check their position thousands of times each second. When the beams reach full speed, they enter special crossover points. At those spots, protons crash into each other. The energy released mirrors the state of the universe just after the Big Bang. Each collision generates a firework of new particles. Detectors surround each collision point. They look like giant cameras built from metal and silicon. Atlas and CMS stand out as the largest, both weighing thousands of tons. They record the spray of subatomic particles that fly outward. Tiny chips capture data on mass, charge, and speed. High-speed electronics convert those signals into data. All systems undergo tests before each run. Technicians monitor every channel to catch any faults. Above ground, engineers operate in control rooms with screens and consoles. They manage beam injections, magnet currents, and safety systems. Thousands of computers collect and process data from every experiment. That information spreads across a global network of data centers. Researchers from over 100 countries log in to analyze results. Teams meet daily to review findings and plan new runs. Scientists focus on a few main goals at CERN. One is studying the Higgs boson, the particle that gives mass to others. Another aim is searching for signs of dark matter, the invisible substance that shapes galaxies. The team also explores how gravity works at small distances. They test if space follows known laws when particles sit in extreme energy. Some theories propose that extra dimensions could exist beyond the ones we see. If a particle enters those tiny spaces, it might disappear from our detectors. Physicists watch for missing traces in their data. A gap in energy readings can hint at new directions to study. Each clue guides the design of future experiments. No test has ever torn open space or created a doorway to another dimension. The collider checks how particles behave under strong forces. Every result goes into open databases for public view. Anyone can review the numbers and charts to see how the experiment went. CERN publishes updates on its website. CERN plans to upgrade the collider to reach higher collision rates and energy levels. The high luminosity LHC will increase collision frequency by 10 times. That will help find rare events that slip past current detectors. Other proposals include a new ring collider that is twice as wide. Each project aims to push science into areas we have not explored. But while physicists saw patterns in particle trails, the internet saw something else entirely. A doorway. Could the world's most advanced science experiment have accidentally sparked a story no one expected? Where did the portal story come from? The story began when someone wrote that they had seen a strange light near one of the Large Hadron Collider tunnels. They described a flicker of color at an access hatch late at night. That statement caught the eye of readers who search for odd science news. Soon, a writer for a satirical site turned the note into a headline about CERN opening a gateway to another world. Many readers took it as fact. Within hours, social media pages linked to the satirical article as evidence of a secret experiment. Video channels looking for shocking topics created posts titled "CERN Portal Shocks Scientists." They used stock images of flashing lights, a clip from a lab tour, and a dramatic voiceover. Each upload promised unseen footage and insider leaks, but offered only the same satirical text, dressed in new words. Search engines also played a role. Early on, searches for CERN Portal returned that satirical link at the top. People reading headlines assumed the site was official. Those headlines reached news feeds of millions online before anyone posted a correction. Websites known for conspiracy claims added more layers. One blog tied the portal idea to ancient myths about hidden realms buried beneath Europe. Another suggested secret military project used the collider to open doors for tests. None of these sites provided real documents. No engineer or scientist spoke on record. Their claims came from quotes that could not be traced to any source. Meanwhile, fact-checking groups looked into the story. They searched CERN press releases, lab reports, and public archives. They found no reference to any portal experiment. Their summaries noted that CERN publishes every technical note on its website. No data file or internal memo mentioned a doorway to another dimension. After reviewing the evidence, fact-check sites concluded that the portal claim was false and based on misread satire. Max Laughlin first saw the headline in a group chat and decided to verify it. He opened CERN's official news page and found a statement denying any portal tests. He downloaded the technical FAQ and noticed a section explaining how proton collisions cannot tear space. Max even made some writings explaining the true work of the collider before heading to the Joe Rogan show. On the podcast, Joe Rogan and Max traced the claim step by step. They described how a casual post in a public forum turned into a viral headline. They replayed the audio of that post, then compared it to the actual text from CERN. Together, they showed how the portal idea grew from a joke into a sensational story. But here's the twist. While Max was busy dismantling internet myths, real physicists were exploring something even stranger. What if the idea of hidden portals wasn't entirely fiction after all? What science says about other dimensions? Physicists have long considered that space might include more directions than the three we see. Early in the 20th century, mathematician Theodore Kaluza proposed a fifth dimension to unite gravity and electromagnetism. Later, in the 1930s, physicist Oscar Klein suggested such dimensions could be tiny loops too small to notice. These ideas laid the groundwork for modern theories that aim to explain forces and particles under one framework. In recent years, string theory has built on those foundations. It describes fundamental objects as tiny, vibrating strings, and it requires up to 10 spatial dimensions. The shapes of those extra dimensions, often called Calabi-Yau spaces, determine the properties of particles. If the shapes differed, the universe would behave in another way. Even so, string theory predicts countless possible shapes. That makes finding experimental proof a major challenge. To test for extra dimensions, researchers seek deviations in gravity at short distances. In a lab at the University of Washington, the UTWash group positions parallel metal plates just a millimeter apart. They measure the pull between them with accurate torsion balances. Results down to a fraction of a millimeter match Einstein's predictions. That rules out large extra dimensions at those scales. High-energy experiments at the Large Hadron Collider offer another approach. When protons smash together, they unleash energy that could detect hidden dimensions. Detectors surrounding collision points record every outgoing particle. Scientists look for missing energy where particles might escape into unseen space. After analyzing billions of collisions, they find no unexplained gaps. These findings set limits on dimension sizes, pushing them below 10 to the minus 19 meters. Astrophysical observations add further constraints. Collisions of cosmic rays in the atmosphere reach energies beyond those at CERN. Telescopes and balloon experiments monitor those collisions for signs of mini black holes, which some theories predict could form if extra dimensions exist. None have been seen. Likewise, the study of supernova cooling and the cosmic microwave background provides indirect tests. Both align with current physics without extra leakage of energy. Dark matter remains a puzzle in astronomy. It exerts gravity but does not emit light. Some models link dark matter particles to extra dimensions to explain their behavior. Underground labs like Xenon 1T and Lux Zeppelin search for rare collisions between dark matter particles and atomic nuclei. So far, detectors record only background events. No clear dark matter signal has appeared. String theory moves the idea further by including all forces in one picture. It treats particles as tiny loops and needs the extra dimensions to make the math work. Each pattern of dimensions leads to different possible universes. Physicists study these patterns to see if any match our world, but the sheer number of options makes the task difficult. Gravitational wave observatories, such as LIGO and Virgo, record waves from black hole mergers. If extra dimensions exist, they could alter how waves travel through space. So far, wave signals fit the predictions of standard physics. Researchers continue to refine experiments with new daily techniques. But what if the missing piece isn't in our universe at all? What if the silence in our detectors is the sound of something slipping away? Could we be watching the wrong dimension? Highlights from the JRE conversation: Max Laughlin opened the discussion by describing how collisions at CERN probe the smallest parts of matter. He explained that when protons smash together, they recreate conditions that existed just after the universe began. Detectors record sprays of new particles. By studying the debris, scientists test theories about forces and the building blocks of everything around us. He moved on to the idea of parallel worlds. Max said that in some physics models, multiple versions of reality coexist. Each version follows slightly different rules. Particles might hop between these versions when energy reaches extreme levels. He pointed to the Large Hadron Collider as one place where such energy appears. According to Max, if particles slipped through to another version, we would notice gaps in the data. Detectors would show missing energy. He reviewed common findings. So far, all missing energy signals match predictions, which puts strict limits on how easily particles could wander off. Next, Max turned to the double-slit experiment. He outlined how particles shoot through two openings and create a pattern that looks like waves. That pattern shifts when observers measure which slit a particle passes through. He used this to support the view that measurement shapes outcomes in quantum physics. He said, the experiment shows that reality at the smallest scale reacts to observation. He said that scientists still debate what that truly means. He then examined the theory that every object vibrates at a certain frequency. In his words, matter is not solid, but energy in motion. He said that vibrations define the properties of particles and forces. When energy levels change, particles can appear or disappear. He referred to the discovery of the Higgs boson in 2012 as a key example. That particle gave mass to others, which explains why some particles move differently. He summarized how the collider confirmed this by tracking Higgs decays into pairs of photons and other particles. Max also addressed dark matter. He said the universe contains far more of this invisible substance than atoms. However, it does not emit light or interact strongly with known forces. Underground labs around the world try to catch dark matter collisions with detector materials. So far, none have produced clear events. He pointed out that collider data could reveal dark matter particles if they appear alongside known particles. No such events have shown up, which narrows the search. Throughout the segment, Max linked clear descriptions of experiments to the bigger questions they aim to answer. He kept the focus on data and results, laying out each step perfectly. He showed how ongoing studies at CERN and other labs test the limits of current theories. His overview captured the state of modern physics, from particle sprays in giant detectors to the subtle measurements in rooms deep underground. But here's the twist. Max's clear-cut explanations only made one thing more obvious. For all we've discovered, the biggest mysteries are still untouched. So, what exactly are we missing? Still unanswered, the big questions remain. Even after decades of experiments, key puzzles in physics await answers. One of the largest involves dark matter. Observations of galaxies and galaxy clusters show more gravity than visible matter can explain. Researchers seek particles that interact weakly with normal matter. Detectors like Xenon 1T in Italy and Lux Zeppelin in the United States use tanks filled with liquid xenon or argon. They wait for rare flashes of light when a dark matter particle collides with a nucleus. So far, these detectors have not recorded definite dark matter events. Each new run raises the bar, ruling out many theoretical candidates. A second question focuses on neutrinos. These ghost particles pass through Earth with almost no interruption. Experiments such as Super Kamiokande in Japan and IceCube in Antarctica track neutrinos from space and nuclear reactors. They found that neutrinos change type, a process called oscillation. That discovery won a Nobel Prize in 2015. However, the mechanism that gives neutrinos mass remains unclear. Scientists plan new facilities like the Deep Underground Neutrino Experiment in the United States. There, a beam of neutrinos will travel 1,300 kilometers from Fermilab to South Dakota. The goal is to measure oscillation patterns with greater accuracy. The search for new forces also continues. Gravity is well described at large scales by Einstein's theory, but it resists a full quantum description. Projects such as the proposed gravitational wave Cosmic Explorer aim to detect minute ripples in space caused by cataclysmic cosmic events. If gravity behaves differently at very short distances, these experiments might spot anomalies. Plans for next-generation particle colliders are underway. The future Circular Collider in Europe and the Circular Electron-Positron Collider in China would reach higher energies than today's Large Hadron Collider. A more powerful collider could produce heavier particles or reveal signs of extra dimensions. It could also recreate conditions an instant after the Big Bang with even greater clarity. Governments and research agencies are still negotiating funding and site locations, but these proposals show the field's ambition. Scientists also wonder why matter dominates over antimatter. Big Bang models predict equal amounts of both, yet our universe is almost entirely matter. The theory of charge parity violation offers a partial explanation. Experiments at CERN's LHCb and at Japan's Bell track decays of particles and antiparticles to spot tiny differences. Early results show small imbalances, but not enough to explain the full effect. Researchers continue to collect data and refine their measurements. Efforts in quantum gravity look to unite general relativity and quantum mechanics. Approaches such as loop quantum gravity and string theory propose different pictures of space and time. None has produced testable predictions that experiments can confirm. Quantum sensors using ultracold atoms and superconducting circuits aim to probe gravity at microscopic scales, where quantum effects might appear. Finally, understanding the Higgs field itself remains a priority. After the Higgs boson discovery in 2012, questions arose about whether the Higgs is part of a larger field structure. Accurate measurements of Higgs properties could reveal interactions with unknown particles. Future collider data and experiments at dedicated Higgs factories will target subtle deviations from current models. While each of these questions drives new research, the answers remain out of reach. Physicists worldwide collaborate on experiments, share data openly, and refine theories as fresh findings arrive. Though the road ahead is long, these unresolved issues guide the next generation of work, pointing to discoveries still waiting beneath the surface. So now, from dark matter to hidden dimensions, we've only scratched the surface. What if the biggest breakthrough of our time is already here, just waiting for someone to see it first?